exemplar I had given you, right? With the help of which I had tried to explain you that there is always a relative motion between the two frames, right?
Yes, ma'am.
Okay, now let's start with the next topic. And we were discussing A5 chapter yesterday, so I'm putting the heading over here, which is Galilean and special relativity. Okay.
Yes, ma'am.
Okay. So after this, the very first topic is event. Okay. Now, what is event? Event is some change that takes place at an point. Okay. With respect to time. Some change that takes place wherever you are getting stuck, Akshita, just stop me in at a point in space at a point in space with respect to time. Okay. After
Yes.
that, we are having observer. Now, what is an observer? So basically, an observer is someone who measures physical quantity related to an event. Okay. So observer
Yes.
is someone who measures the some physical quantity to an event. Okay. Like yesterday, I had given you one example. Do you remember that? That suppose here a person is standing, car is going, and from
And
here,
there was a flight.
yeah, flight is coming. And suppose here we have an aeroplane. Okay. And with respect to that, I had explained you that if suppose it is traveling with 100 meter per second, this is traveling with 20 meter per second and the person is at rest. So here let it be A, let it be B, let it be C. Okay. So I had told you that as per A, the velocity of this is 20 and the velocity of this is minus 100. Correct?
Yes, ma'am.
Yes, Akshita. Because it is standing at rest, so the total force acting over B object is 20 meter per second, and he observe it as going. Whereas this one he will observe as coming minus. Correct? As per B, the velocity of this particle will be minus 20 per second. It is coming from the opposite direction towards it, isn't it? Because this
Yes,
object
ma'am.
is going in this direction. So, as per him, this object is going away from him at the speed of 20 meter per second. Making sense?
Yes, ma'am.
Okay. So, basically, what is happening over here is as per B, this particular object is going away with a speed of 20 meter per second where the plane is coming towards it. Plane is coming towards it. The vehicle is going in this direction with 20 per second and this is coming in this direction. For the car or bus, whatever this will be carrying this speed. Okay. And this will be carrying minus 20. Shita,
Yes, ma'am.
any doubts?
No, ma'am.
Okay, great. So nothing to be repeated, right?
Yes, ma'am.
Okay. So now, as per this, what is an event? Event will be something like, if suppose this is giving a flash out, okay, then the flash of this would be an event, that the car is throwing flash of the light which is actually traveling. Because what is an event is some change, okay, that is taking place at a point with respect to time. So I would be saying that, yeah, at 100th of the second this bus has started to turn on the lights. Understood, Akshita?
Yes.
Great.
Yes,
Now,
ma'am.
as the observer, like if I say A, the observer, A in position and B flashes the light. Okay. So A is the observer. Understood? Who had seen the event? Understood
Yes.
any? Great. Now we were discussing frames of reference. Okay. How you will say what is the frame of reference? Okay. So let me tell you about the frame of reference also. After this, a little bit idea about what type of frames of reference do we have. Okay. Let's talk about that. Wait, let me give you one. Okay. Yeah. Okay, I'm showing you one picture just to have a look over this.
Yes.
Okay. Check. Is it visible?
Yes, ma'am. The
The
clock.
yeah.
And
Basically, it shows a frame of reference. Done. What is a frame of reference? The construct is it which provides you the position of a given object. Okay. Now,
yes.
coordinate system is covered here in the clocks that an observer uses to measure the time and position of an event. Okay. It
Yes,
is
ma'am.
covered in clocks so that basically what we can do, we can measure the time that an event took place, where it took place, and like that. Done.
Yes.
Okay. So if we used our on clock, let's say, so we would always measure a time that was a little late, isn't it?
Yes,
When
ma'am.
you are having a stopwatch in your hand and you are trying to measure the oscillations, always it happens that Akshita, you become late due to that. Maybe while measuring the time period of the oscillation or in any event related to that, right?
Yes, ma'am.
Okay. So basically, we would always measure a time which will be a little bit late since it takes a time for the light to get from the event to us. Okay. Here one event is happening. Can you see this? The time at which this clock is settled here, the flashlight came. It's 9. That's what I can see. Whereas if I'm standing here on the earth surface, suppose it comes to us after 5 minutes. Can you see that? Check.
Yes, ma'am.
Isn't it? So
Yes.
observer can only make the measurements in their own frame of reference, but not at that frame of reference. Are you getting that?
Yes, ma'am.
So this is the play of frame of reference. Why do we need frame of reference? Because obviously this flash of light is taking place at 90 million kilometers away from the observer. Try to understand this factor very clearly, Akshita, that this event is taking place at a 90 million kilometers away from this girl. So, what is happening? The flash of light exactly came at 9, but when she observes, because it takes a time to travel this much of the distance, she had observed it at 9:05. Making sense?
Yes, ma'am.
So frame of reference matter?
Yes, ma'am.
Okay. So space and time are related quantity. They are never perfect. They are never exact. First thing. Understood?
Yes, ma'am.
Okay. Now let's come back to this particular picture. Okay. Here we have three observers, suppose. Okay. They are sitting in three different frame of reference. Let's say this one is sitting in this frame of reference. Okay. I'll draw it. A particular picture. This is sitting in this particular frame of reference. Okay. Where a particular frame of reference. Making sense? Okay,
Yes,
so we can see that the moving, but woman is standing still. True?
yes, ma'am.
Okay, now this is because we often measure to the earth and she is stationary. Correct?
Yes, ma'am.
Okay, yeah. So what is happening here? But if suppose a person who is sitting inside the car, okay, A is moving away from him at a speed of 20 meter per second, okay, done. This thing that I
Ma'am.
had explained you. Am I making sense,
Yes, ma'am.
Akshita?
Yes, yes,
Yeah.
ma'am.
Now, is there any experiment that we can do to prove one of them is moving and one of them is stationary? Means which one is standing, which one is moving? Can we make any assumption, any experiment? Tell me. Because see, with the perspective of A, they both are moving. With the perspective of B, they both are moving. The woman and the plane. But as per A is standing still. As per our frame of reference, also, if I see this woman is standing still, this is moving in this direction, this is moving in this direction, correct?
Yes, ma'am.
So, can you tell me any one experiment where we can prove that which one of them are moving and which one of them are stationary? Yes, go ahead,
Uh,
Akshita.
by
Hmm.
calculating the total distance of uh, all the uh, objects, for example, like here, if we take the car with respect to the plane, if someone is telling that the girl is moving, and uh, if they add the speed of her, like, and the car, I think it would be lesser than the car and the
Mhm.
plane. So, but I am not sure, ma'am. I am just like guessing.
Yeah, it's okay, it's okay. You are just guessing. I can understand that. It's okay. You are just guessing, right?
Yes, ma'am.
Yeah, not an issue. Not an issue. From the yesterday's class also, do you have any doubt?
No, ma'am. I'm still doing questions.
Hmm.
Can I tell you tomorrow, ma'am, with the doubts? Can I?
Yeah, sure. Yeah, sure, sure. Not an issue. You can tell me tomorrow. Not an issue. Fine. You can tell
Yes,
me about that. But you are going through all of them, right? Because we had
yes,
completed one chapter and you should be aware that what you are doing. Done? Now, let's come to this part. Basically, see, when we look at this particular picture, we can see that the car and the plane are moving. Okay, but the woman is standing still. That is what I had explained to you. Now, the presence of earth can be very, very confusing, you know. Why? Because we are always thinking that the person is at stationary position, but exactly what is happening, Akshita, that earth's gravitational field and the fact that it is spinning is a complicated matter. Are you getting? That
yes,
means
ma'am.
we are not standing still, we are spinning. Right. I mean, for this reason only, we will now move and the observers into the space, as in, like we had calculated for this picture. This picture is showing you the same thing, isn't it?
Yes, ma'am.
Okay, so because of this reason only, basically what happens is we do not have any experiment, I guess, where we can say what exact person is doing with respect to anything, because until and unless we are not considering Akshita, our position to be standing still, we are not able to identify the types of motion. See, you were in grade 7, grade 9, grade 10 when you were doing the Newton's laws of motion. In that, we had only studied that, yeah, with respect to me, whatever events I am observing as an observer, I am standing still and I am observing them. And hence, VAT equations, laws of motions are being applied over that. Making sense?
Yes, ma'am.
Okay. But whereas that is not true. When Einstein came, what did he say? He said that no, we are moving. Earth is exactly spinning. So our frame of reference is actually, I should say, accelerated frame of reference. Right?
Yes, ma'am.
So we are accelerating continuously. Okay, but for a standard condition, we can assume to that something is moving and we are standing still. Okay, let me give one more example out of this. Okay, wait. Suppose, uh, yeah, here. Consider this picture. Okay, Akshita.
Yes, ma'am.
This was picture 2. This is picture 3. Here, let's say my A and B. Okay, understood? No, they take a
Yes,
ball and they place it on the floor. Okay, now when they apply the force to the ball, it will accelerate, isn't it?
yes, ma'am.
And if they do not, it will remain at rest, isn't it?
Yes, ma'am.
Okay, so that means Newton's laws of motion apply in each frame of reference, that is in A as well as in B, whereas you can see that A is non accelerating and B is accelerating. Making sense?
Yes, ma'am.
See, this is moving with velocity v. So it is
Yes,
accelerating, isn't it?
yes, ma'am.
Whereas this one is non-moving. So this will be non-accelerating. Correct or not?
Yes, ma'am.
Any doubts that you are facing?
No, ma'am.
Great. So Newton's laws of motion apply in each frame of reference, but there is in fact no experiment that A and B can do not show who is moving.
Yes, ma'am.
Okay, there is no such experiment. Understood? They are moving related to each other. Are you getting?
Yes, ma'am.
But there is no absolute movement about both of them. I hope I am making you understand clearly.
Yes, ma'am.
Now, this particular phenomena is known as inertial frame of reference. Okay. Are you getting, Akshita? This particular
Yes,
phenomena is known as inertial frames of reference. Done?
yes,
Now, let's say the same experiment now I am doing when this rocket is moving. Let me show you, like, if I have. Yeah. Check this. It's moving now. The rocket is on fire. And now the B person. Where is the B person? Here it is. It was moving with V velocity. Here is the ball. A was at rest. Understood, no, Akshita?
Yes, ma'am.
Yeah. Now see here. This rocket is also moving. Okay. Now the ball is moving in this side and the rocket is moving in this side. I hope I am making you understand with this picture.
Yes, ma'am. Yes, ma'am.
Okay. Done. So now, if you look at this observer B, Akshita, that now places a ball on the ground, it will start to roll towards her, isn't it? As the rocket is moving in the right hand side direction, okay, even though there is no force acting on the ball, correct?
Yes, ma'am.
Okay. Can you tell me the reason?
Because uh and there is no force acting on the ball because the rocket is moving towards the right, so uh the the uh the event happening here is the ball, but generally, like when the rocket moves forward, the pressure from the rocket makes the ball move backwards.
Which Newton's law has been applied over here?
This will be third law. Every action has an equal and opposite
Has an
reaction.
equal and opposite reaction. So that has been applied over
Yes.
the rocket. No, why it will be applied over the ball? Rocket is moving in the right hand direction. So the
Because of
air
the
resistance
rocket.
will push it in the
Because
backward direction, right?
yes, ma'am.
What? Isn't it? As per my
Yes, ma'am.
understanding, if the rocket is moving, the Thara rocket is moving in the right hand side direction, then not the ball, but the air resistance will going to push the rocket in the left hand side direction, isn't it?
Yes, ma'am. I said because of the rocket, not the ball.
Okay. So basically, see, when you watch it from the outside, okay, we can see that what is happening, that the rocket is moving towards right hand side direction. Okay. So basically, here, Akshita, Newton's laws do not apply. Okay. It is a force which is acting on the rocket, which pushing it in the past the ball, right?
Yes, ma'am.
That is what you said. And the ball is stationary.
Yes, ma'am.
Correct.
Yes,
Newton's
ma'am.
laws have not been broken, but inside the rocket, it appears that they have been. Are you getting my point? They got molded, Akshita. They got molded. The laws got molded. Why? Because here the force is pushing. Means basically you had only given the answer and you had actually conveyed me that, ma'am, it's the on the rocket the backward force is applied. The ball is still at stationary, but due to that force only, it appears that it is going towards the person.
Yes, ma'am.
So, when you are standing in an accelerated frame of reference, Akshita, from this you can actually justify the statement that when you are standing in an accelerated frame of reference, you can see that an equal and opposite force is also been applied over any object, and that seems to be moving in the opposite direction. Yesterday also I had given you a lot of examples that when you swing the circular round wala swing, in that you must have observed that we experience a force in the outward direction.
Yes, ma'am.
Remember, in that case also I had given you an example that the centripetal force is acting
Yes.
towards the center along the radius. Yeah.
Yes, ma'am.
And also when the two girls who are playing like this,
The swing, the round and
yeah,
round.
yeah, this I don't know the name of the game, but when you do this thing also, what happens is you if you leave the hand now, you will fall outward.
Yes.
Okay. So as soon you come in the accelerated frame of reference, The Newton's laws does not get break, but it appear like they have got broken. Okay, so these accelerating frame of reference like this are known as non-inertial frame of reference. Are you getting?
Yes, ma'am.
Okay, so this one was inertial and now this one is non-inertial. Any doubts in the frame of reference?
No, ma'am.
Exactly clear with you that what we are discussing and how they are wrong and correct?
Yes, ma'am.
Yeah. Just give me a sec, Akshita. Just 1 minute. Akshita, check this
Yes, ma'am.
question. Can you see this?
Yes, ma'am.
Yeah, it is related to inertial and non-inertial. Right? The answer?
Person sitting inside a bus that is moving at a constant velocity. Inside a bus. Is the bus an inertial or a non frame? Constant. Uh, hmm, since the bus is at constant velocity, I think it is uh, inertial. Passenger in a bus suddenly backward, falls backward when the bus starts moving. Explain this using the concept of frame of reference. Suddenly starts moving backward.
Say it again. Say it again. Frame of reference what?
No, I'm just reading the question. One-
No, it's very easy. A person is sitting inside the bus and that is moving at a constant velocity. Is the bus is an inertial or non-inertial frame of reference?
First
Justify
one,
your answer.
first one is
Hmm.
inertial. Uh,
Hmm.
justify. So, mm,
Because the object remains at rest or in uniform motion unless it is acted upon by a external force as per Newton's first law.
okay.
Okay. Yeah.
Yes.
Read the second question now.
A passenger in a bus suddenly falls backward when the bus starts moving, backward and moving. Explain this concept using the frame of reference.
Hmm.
This is the third law, ma'am. Again, uh,
Okay. Give the explanation.
one second, ma'am. So, passenger in the bus suddenly falls backwards.
See, when the bus starts moving, Akshita, it accelerates, right?
Um,
Making it a non-inertial frame of reference, isn't it?
when the bus starts
Now,
moving,
in this frame, yeah, now basically in this frame, a pseudo force appears to be acting on the passengers in the opposite direction of acceleration. Clear?
yes, ma'am.
However, from the inertial frame of reference or from the ground when something is observing, the passenger tends to remain at rest due to inertia.
Yes, ma'am.
Okay? While the bus moves forward. Correct?
Yes, ma'am.
Okay. Now this makes it appear as if the passengers are falling backward.
Yes, ma'am. Since they are still in the bus, not moving,
Hmm.
but the bus
Yeah,
is
exactly.
moving.
Hmm. Hmm. Go ahead. Go ahead. I'm listening.
So, that's why the passenger kind of feels like they're like falling
Hmm.
backwards. Uh,
Yes. So basically, you understood now how to explain them.
yes,
Now,
ma'am.
can you write one answer for me? And then you can give me the explanation. Okay. Akshita, are you
Okay,
there?
ma'am.
Yeah.
Yes,
Need to be very
yes,
quick. I'm
ma'am.
just giving you
Yes,
2 minutes of the time. Okay. Just think of it and then explain it. Be quick. Write the answers.
ma'am. Since it is accelerating forward, it's not constant acceleration. It's a non-inertial frame of reference. Uh, Describe the motion of the ball as seen by the person inside the train. Inside the train, this uh, c- inside the train, which is like similar to that bus. So it is non-inertial. Outside the frame, outside the train, outside the train.
Akshita, give me the full fledged answer now.
Oh, one second, ma'am. Like I'm not sure of outside the train thing.
Hmm.
Uh, the ball, if I am standing outside the train, I would feel the ball is uh
Hmm.
coming forward. Drop inside a train means like randomly drop, na? I am
Okay.
not
It's okay. It's okay.
inside
Listen,
the train.
there
It is
will be two references. Hmm.
inside the
There
train.
will
It
be
is
two references, Akshita,
out.
inside the train and outside the train. Inside the train, it will be non inertial, right?
Yes,
Accelerated, isn't it?
yes, ma'am.
Whereas outside the train, it will be inertial. Correct? So let's
Because
talk
the
about
ball.
inside the train.
Okay.
Okay. So question is, a ball is dropped inside the train that is accelerating forward. Describe the motion of the ball as it is seen by the person inside the train and by the person standing outside the train. Okay. So when we talk about inside the train, the ball appears to fall in a curved backward path. Okay. Because the train accelerates forward and the ball moves down. Isn't it?
Yes, ma'am.
Ball is dropped, no? So it will be appearing like uh,
Can you
it
draw like?
appears to be like, suppose this is bus.
Yes.
It has been dropped from here. So it is
Okay.
moving in this direction. So it will be appear to be falling here.
Yes, ma'am.
Making sense?
Yes, ma'am. So it will be non-inertial
Okay.
on the
Yeah.
inside.
Okay. So here a pseudo force is seems to be acting in the backward direction and hence it is falling like that. Please make the words clear, Akshita. How I am making the statements. Is it audible to you clearly? No?
Yes, ma'am.
Very good. So, therefore, if a person is standing outside, the ball will fall vertically down under the gravity and there will be no external horizontal force acting on it.
Yes, ma'am.
Okay?
Yes, ma'am.
Whereas, if a ball is seen from the inside of the train, it appears to be falling in a curved backward path because the train accelerates forward while the ball moves down. Okay, so a pseudo force seems to be acting on the ball in the backward direction. Clear?
Yes, ma'am.
Okay, so this is what is given over there. Okay, yeah. Now let's come to the picture, that is this. I'm writing it from here now. Okay, so next topic is Galilean relativity. Listen very carefully. What is Galilean relativity now? Just a second. Yeah. So, what is Galilean relativity? Basically, Galileo did see many experiments, Akshita, with both live and dead objects. Okay. And came to the conclusion that basic laws of physics are the same in all inertial frame of reference. Okay. Akshita, am I audible? Hello, Akshita.
Yes, ma'am. That is a slight taking, but it's yeah. I can. Hello, ma'am. One. Hello, ma'am.
Yeah. Yeah, you are audible. Akshita, your end is making some glitch. Is it like that? Shall I
Ye-
wait?
Yes, ma'am. I will just rejoin, ma'am. 1 second.
Yeah, sure. Take your time.
Hi, ma'am. Is it fine now? Hello, ma'am. Hello, ma'am.
Yes, you are audible.
Okay, ma'am.
Yeah, tell me. You were saying something. Yeah, tell me.
No, ma'am. I was just like, your voice was just cracking to me, and now it's fine.
Yeah, from your end, your voice was not at all coming. So maybe due to technical glitch only.
Yes, ma'am.
Okay, done. So now I'm repeating it. that Galileo did many experiments, Akshita, with both live and dead objects and came to the conclusion that the basic laws of physics are the same. Okay, for inertial frame of reference, only for inertial frame of reference. Okay,
Yes.
I'm writing it over here. If you are getting confused, Akshita, please pay attention. Wait. Check. When I speak about inertial frame of reference, your A will be equal to 0. Okay. Hence, force applied on any object will be 0 or constant. Okay. Due to this, you will see either uniform motion
Yes, ma'am.
Yeah. So basically, either you will uniform motion or you will see no. That is at rest. Understood?
Yes. Yes, ma'am.
Okay. And in this frame of reference, Newton's laws are verified. Okay. They are
Yes, ma'am.
working. Understood or not?
Yes,
Any
ma'am.
doubts?
No, ma'am.
Okay. So here, after this, we are having coordinate transformations as per Galilean relativity when we convert these inertial frame of reference into non-inertial frame of reference. Okay. Now let's take the first picture again that we had discussed for the aeroplanes. Wait, let me give you that pictures. Is it visible to you what I'm showing?
Uh, the picture, ma'am, is ma'am.
Is it visible?
No, ma'am. No, ma'am. I can't see it.
What is visible to you? Tell me.
I can't see any picture. Lastly it is uniform motion, no motion rest.
Is it like that?
I think now you upload
Now,
now I think now you upload a picture. Now it is showing up.
can you see this whiteboard now?
Yeah, yes.
Which page is visible to you now?
Zoom.
Okay, done. Done. Fine. So basically, it's only visible to you when I'm sharing my Chrome, otherwise, it's not visible. So I have the Chrome only with. Just wait, this picture is taking too long to get up. I'll share it over here. Now check this one. Okay. I'm discussing this again. Okay. So basically, if the observer B been used in this picture, okay,
Yes.
A and B observers are there, na, and they both are measuring the position of the blue balloon. Can you see that?
Yes.
Which
Ma'am.
is floating weightlessly. This is the blue balloon, which is
Yes, ma'am.
okay. Then they will get different values, obviously, because it's at rest and B is moving in this direction with V velocity. Correct?
Yes, ma'am.
Yeah. So if B were to tell A that where is the ball? Where is the ball? Right? It would not make any sense unless A knew how to transform B's measurement into her own frame of reference.
Yes, ma'am.
I'm saying all the things again. Please listen very, very carefully, Akshita. This chapter is not very tough. It's just that you need to understand what we are doing.
Okay.
Okay. So just try to understand factor. I'm saying that I'm having two observers over here, A and B. This spaceship is at rest and this spaceship is moving in right direction. And here one balloon is floating, weightless balloon is floating inside it. Can you see?
Yes, ma'am. On B.
Yeah, done. So if the observer A and B are in the spaceships and they are at the positions of they measure the position of this blue balloon, okay, which is floating weightlessly in the spaceship B. Okay, then it is
Ma'am,
like floating just nearby to it, right?
your voice kind of again it went like I couldn't hear you. Like
Now is it audible? Now is it audible?
yes, ma'am. You said like two. You are saying and then it just went. Can you like?
Okay. I'm repeating. I'm having two observers A and B. Okay, in the
Yes.
spaceship, and both measures the position of the blue balloon.
Yes.
Okay, this blue balloon is floating weightlessly in the spaceship B, right? But
Yes, ma'am.
as per A, it is quite away. As per B, it is nearby. Correct?
Yeah. Yes, ma'am.
Okay. Now, if B were to tell A that where is the ball, B is asking A, where is the ball? Then it would make no sense unless A is aware how to transform B's measurement into her own frame of reference.
Yes, ma'am.
Because this is at rest and this is moving, so it will
Yes.
make non-inertial frame of reference and this will make inertial frame of reference, correct?
Yes, ma'am.
Okay, now A knew how to transform B's measurement into her own frame of reference. Suppose, then it will be known as Galilean transformation. Are you getting?
Yes, ma'am.
If A giving the position of the balloon or the ball, whatever it is, by transforming B's coordinates into A coordinate, now this transformation will be known as Galilean transformation.
Yes, ma'am.
Got it or not?
Yes, ma'am. I got it.
Very good. And thank you. Now, at some time, as A and B are apart, okay, A and B are apart, correct?
Ma'am.
Akshita,
Ma'am.
yeah, you are on. Say yes now whenever it's like I'm asking something.
Yes, ma'am. Your voice just like again it disappeared and came back.
Still, it is my end now. The network is quite
Now,
well.
oh, I think it's from my place, ma'am.
Oh yeah, it's okay. It's okay. No issue. No issue. Because maybe due to the internet glitch, it may be happening. Not an issue. Okay. Yeah.
Yes.
So I'm saying all the things again. Just do have a look at this picture. Do
Yes,
you
ma'am.
have any other class now?
No, ma'am. I understood this part, Galilean transformation from B to A. After that, you said something, ma'am. What did you say? Like,
Yeah, I'm explaining. I'm explaining. Explaining. Don't worry. Check this picture.
yes,
Okay.
ma'am. Yes, ma'am.
Done. So I was telling is, let's say it's the thing is going in this direction for B. A was standing stationary, right?
Yes, ma'am.
A is standing stationary, B is going in this direction. Now let's say the particular spacecraft is shooting out a flash or any pop is been visible by B. Okay. So this frame of reference is at rest. This frame of reference is moving. S is the rest position. S dash is the moving frame of reference. Okay.
Yes, ma'am.
Distance between the two, let's say, is X.
Yes, ma'am.
This is moving with velocity v. The distance between them will be vt. Why? Because you are aware, Akshita, that speed equals to distance over time. So what is distance? Speed into time. Right?
Into time.
So I am
Yes, ma'am.
measuring the distance. So it will be speed into time. Okay?
Yes. Yes, ma'am.
Any doubt in this picture?
No, ma'am.
Great. I knew that A and B measured the time and position of the event of this pop. Then to this, they will use the clock and in their own frame of reference, but to transform the measurement, they need to have, I guess, some reference points. Correct or not?
Yes, ma'am.
That where this pop out is happening. For that, they need to have a reference point, Akshita. That yeah, from this position it is happening at 10 meter. From this position it is happening at 100 meter. Isn't it?
Yes, ma'am.
Okay. They must be having some frame of reference. Then only they can measure these events. Right. So let us assume that at the time when they started their clocks, the two frames were at the same place. Okay.
Yes, ma'am.
Okay. Now this is not really possible with the rockets, but we can imagine it. Okay. We can imagine it. Okay. If we call A's frame of reference as S and B's frame of reference as S dash, we can say that between A and B's measurement, what is the similarity and dissimilarity? Okay. Are you getting?
Yes, ma'am.
Okay. So now I'm converting these frames of reference and I'm explaining you about Galilean transformation. Listen very carefully. It's very, very important. Okay.
Yes, ma'am.
Okay. So in this Galilean transform, one frame of reference is for A, that is S. One frame of reference is for B, that is S dash. How they will transfer, that I am writing here. Transformation. Okay.
Yes. Yes.
F transformation I'm writing. So X axis will remain axis, but transformation will be happening X dash plus V is at a distance of Vt from this. So X dash plus Vt added as per the A observation for B. Akshita.
Ma'am.
Yes. Akshita. Am I audible? Akshita. Am I audible? Your voice is not audible.
Hello, ma'am. Can you hear me now?
Yeah, now
Hello?
it's audible. Yeah, you are audible. Relax. Okay. Yeah. So I was telling, as per A, the frame of reference is X. As per B, it is X dash. Correct?
Yes, ma'am.
Transformation will be done as X dash plus VT. Correct? See, on X axis is moving. B is standing at this position, no? At VT distance. So X axis will show plus VT distance in the transformation.
Yes, ma'am.
This is moving with X dash direction. Moving with X dash in X direction. Are you getting no?
Yes, ma'am.
Yes. So as per X axis, if I am calculating from A's side, you need to add VT in X dash for transforming the coordinates.
Yes.
Clear? Okay. Now let's talk about Y axis. Y axis is not going anywhere. So we'll Z also not going anywhere. So Z will remain Z only. T is not going anywhere. T is always same. T will remain the same only. Any doubts?
No, ma'am.
Sure.
Yes, ma'am. Sure, ma'am.
Okay. So I am actually I had tried my level best to explain you a non-inertial frame of reference, Galilean and special relativity. And see, these pictures will are giving you I should say that explanation of everything. If you are facing any doubt, just do Akshita.
Yes, ma'am.
I
I'll just
hope
go.
I had made you understand
Yes, ma'am.
till
I'll just
Galilean.
write
Okay.
this part alone. 1 second, ma'am.
Yeah, sure. Right. It. So from tomorrow, I will start the other transformations also. Okay.
Yes, ma'am.
Okay. How many classes we had done till now, Akshita?
I will check and I will let you know, ma'am.
Yeah, it's okay. It's okay. No issue. Because even I am forgetting. See, tomorrow and day after tomorrow, I'll be on my holiday. So if you want, we can conduct the extra classes also. Okay. That's why I was asking. In the
Yes, ma'am.
morning schedule. In the morning schedule. Okay. So we can have like two classes in one day so that we can finish it. Okay. Because in
Yes,
this week, in the last week, I had skipped one class due to my fever and all that stuff. Okay. So if you are available, just do let me know via Miss Sonia and I'll be taking your class. Okay.
okay, ma'am.
Fine, Akshita. So this
Yes,
is it for the day. Okay. Bye.